Welcome to the online video lecture series of the course Computer Organization and Architecture. In the present unit, we have discussed about various instructions which are executed in a single bus architecture of the system, and we have also talked about how control steps can be written for a particular instruction. If any instruction is given, how different micro instructions are executed, and what are the control steps. And we have also talked about program control, and we have also talked about hardware control and microprogram control. Now, in this particular lecture, we will discuss various numerical problems which are important in respect to the problems with respect to the various exams. So, in this first problem, let us talk about first problem. The instruction given as add num r1. What does it mean? This instruction says we have to add the content of register r1 with the content of memory whose address is given in the second word of this particular instruction. So, in this problem, there are two words. Assume that the instruction consists of two words. The first word specifies the operation and the addressing mode, and the second word contains the number. So, that means we have to fetch this particular operand from the memory, and this operand will be added into the ALU with the content of register r1, and final result, which is the addition of these two operand, will be loaded into the register r1 back. So, how this operation is to be carried out through this system? So, as we have discussed already, you have to remember this particular architecture or single bus architecture where various components are connected, like MAR, PC, MDR, Y, ALU, general purpose registers and instruction decoder. So, as we have already discussed in our previous lectures, how instruction is fetched from the main memory and it is decoded, and after that various micro signals are issued by the control unit, either in terms of hardware or microprogram control. So, various control signals are to be issued according to the given instruction. So, in this particular instruction, we can see we have to perform the addition operation and we have to fetch one operand from the memory. So, as we have already discussed, the first three steps are common to all type of instruction. First three steps are related to instruction fetch. We have already discussed in our lecture. In previous lecture, we have already discussed how to fetch particular instruction from main memory, and in parallel to that, the program counter will be incremented by 1, or it is incremented with some offset value. So, as problem says, it has it has two words in the main memory, and the second word, that is the data or the operand value, which has to be fetched from the memory and it has to be added with content of r1 register. So, we have to fetch this value num from the main memory, and this can be fetched from main memory with the help of program counter. So, once the instruction I is fetched from main memory in parallel to instruction fetch, the program counter is incremented by 1, PC equals to PC plus 1. So, who will provide the address of the data? Num, the program counter, because when this instruction was fetched, program counter was incremented by 1 or updated. So, program counter will provide the address of this num value. So, here PC out, because these three steps are related to instruction fetch, and here we have done PC equals to PC plus 1 or some offset value. So, PC will have the updated value or the address of this data num. So, PC out and MAR in, then read signal will be issued. So, PC out gate will be enabled or opened and MAR memory address register in gate will be opened. So, there will be a path from PC to MAR through out and in gate, out gate of PC and MAR in gate of MAR memory address register. So, whatever address is to be transferred or the data has to be fetched from memory, the memory address register is used. Address are transferred through MAR and corresponding to that address of memory, the data will be transferred through MDR. So, because this operation is a read operation, so we have to provide or the read signal will be issued, and here some offset value, then add, then Z in, because PC is connected with the ALU and this has to be incremented by some offset value. So, in parallel to this fetch operation, the PC value will be updated with some offset value. So, this addition operation will be carried out into the ALU. Now, the wait for memory function complete signal will be issued in next step, and once the memory function operation is over, the data is available with MDR. MDR register will be used to transfer the data from memory to processor or processor to memory. Now, this PC is updated. This increment of PC value is done here in step number 4, and this PC value is updated with PC plus some offset value in step number 5. We have done this. Now, the data is available with MDR. This data will be transferred to Y register, because in ALU there are two inputs, one through Y, that is pin number A, and one is directly through the bus, that is pin number B. So, we have to provide two operands, one at the A pin number and one or the second operand at pin number B. So, MDR out, that is the memory content or num value, is provided to this Y pin or this A pin through Y register, and in next step the R1 value is required. So, R1 out gate is open. Now, this R1 is connected with pin number B, because this is connected through the bus at pin number B of ALU. Now, we can perform simple add operation and the result of add value will be transferred to Z register, and from where Z out R1 in means this result has to be transferred to the R1 register back. So, Z out R1 in and then end. So, this way we can perform the operation of add num R1. In next problem, this num is the address of operand. So, we have to perform 2 times the fetch operation. First, we will go to the num location, and in second step at the num location we have to fetch the content or actual operand. Now, in bracket it shows it is an address. In previous case it was the value or it was the data which was stored in memory. Now, in this particular case it is an address from where we can get the second operand. So, this is operation add address of num comma R1, and after performing this operation the result value will be stored in R1 back. Now, we have to provide we have to do 2 times fetch operation in this case. First, the fetch of this particular address where we can get the address of second operand. So, as I said, first 3 steps are common to all type of program. These first 3 steps are simple instruction fetch step, and in parallel to that the PC value is updated by 1. PC equals to PC plus 1 means the address of next word in the main memory. from where we can get the address of this particular num address. So, PC out, like in previous case as we have done PC out MAR in read operation. So, likewise we can do the same operation. The address is provided by the PC and that has to be transferred through MAR, and read signal will be issued and PC will be incremented by some offset value. PC equals to PC plus some offset value, and this PC is updated and we have to wait for memory function complete. Once the memory fetch operation is over, that the data is available with MDR. Now, as I said, this is an address, because in this particular location num value is an address in this particular case. So, MDR will be MDR value will be an address of operand. So, again we have to fetch, we have to perform the fetch operation. So, this MDR out and MAR in, we have to provide a connection or a path between MDR and MAR in through out and in gate of MAR. So, the data of MDR, which is an address, will be transferred to MAR and the read signal will be issued. And in parallel to that, once the read signal is issued, memory function operation or memory fetch operation is going on, and in parallel to that we can transfer the second operand, that is R1 in this case, to this Y register. This operand will be available with Y register, because there are two pins as I said earlier. So, operands will be transferred through these two pins A and B. So, once during the memory function complete or fetch operation, we can transfer one operand to the pin number A through Y register. So, as we have done as we did in step number 7. In next step, the fetch operation is over, the data is available with MDR, means for example, this location is shown here, the location of operand is shown here. So, from this location we go to the location of operand, and this operand data is available with MDR, and MDR will be connected to pin number B. So, simply MDR out, opening the gate of out of MDR, and we perform the add operation or addition operation, and the result will be transferred to Z register, and from where this can be transferred back to R1 register. This way we can perform the operation of this instruction. Next problem is related to pipeline system. In this case, in certain the problem is stated that in this particular case we have to perform the 2 addition operation and 1 multiplication operation as shown here. This is the instruction which we have to perform 6 times. So, we have to design a pipeline system which can perform such type of operation. Here you can see these are 2 operands which are totally different with the operands given in this particular bracket C and D. So, A plus B operation is totally differ with C plus D operation. So, we can perform 2 addition operation in parallel to each other. So, 4 registers are required which can store these operands. So, first R1 register will store A value, R2 register will store B value, R3 register is used to store C values, and R4 is used to store D values. This way we can transfer the 2 operands at a time in one adder, and in second adder 2 operands, that is C and D, we can transfer to R3 and R4 register. So, these 2 addition operation we can perform in parallel to each other. However, the result of these 2 addition operation will be multiplied to each other in a multiplier. So, that is why R5 and R6 registers are used to hold the intermediate result of these 2 adders. So, these are interface, or you can say these are intermediate registers which are used to store the partial results or the intermediate results of these 2 adders. So, R5 and R6 will be used to store these intermediate results, and finally 2 operands, these 2 operands will be transferred to this multiplier, and from where we can get the final result of this operation. So that we can perform in 6 time or n number of times. This way we can design the architecture of pipeline system which can perform such type of operation. Now, the next problem says a non-pipeline system takes 50 nanoseconds to process a task. The same task can be processed in a 6-segment pipeline with a clock cycle of 10 nanoseconds. Determine the speed up ratio of the pipeline for 100 tasks. What is the maximum speed up that can be achieved? So, here in this case we have to find out the speed up factor. First we need to calculate how much time is needed to process these number of instructions or tasks in a pipeline system and in a non-pipeline system. So, that we can compare here and we can find out the speed up factor. So, in this particular problem it is given for non-pipeline system it takes 50 nanoseconds to perform or to execute any given instruction, and there are 6 segments, means the whole system is divided into 6 segments, 1, 2, 3, 4, 5 and 6. So, there are 6 segments. The non-pipeline system is converted into 6-segment pipeline system. So, k value is 6 in this case. We have already discussed such type of architecture or pipeline system in previous lecture of this unit. So, we know what is the formula of speed up factor and we have already derived the speed up factor value. So, in this case the pipeline system clock period is 10 nanosecond and we have to perform 100 tasks. So, simply we can put these values into the formula Ntn upon k plus n minus 1 times Tp, and finally we will get 4.76 value. So, and what is the maximum speed up factor which we can achieve? So, we assume that for infinite number of instruction k plus n minus 1, that is equivalent to n. In that case S max will come as Tn upon Tp. We have already derived this formula in previous lecture. So, simply put the value Tn equals to 50 and Tp equals to 10. So, the maximum speed up factor that we can achieve is 5 in this case. So, next problem. In this particular architecture, we can see it is a pipeline system and we have to calculate various things. So, here this is the memory fetch operation, means we have to fetch some content from the memory and we have to store in A values in R1 and B values in R2, and then these two values are multiplied here in multiplier, and this result will be added with R4 values here in adder, and final value is stored in R5. Here you can see the fetch operation will take 40 nanosecond as given in this problem, 40 nanosecond for memory fetch operation, and this multiplier will take 45 nanosecond to perform its task, and this 5 nanosecond is used to transfer the intermediate result from multiplier to these interface registers R3 or R4, and this stage will take 15 nanosecond to perform its task. So, first, what is the maximum clock cycle time that can be used? As we have already done, the maximum clock cycle will be nothing but the slowest stage time period plus interface. So, tau max is nothing but the slowest stage, that is 45 in this case, and plus interface time, that is 5 nanoseconds. So, it will come as 50. And in second case, it is asked a non-pipeline system can be performed the same operation by removing R3 and R4. So, R3 and R4 registers are removed. So, obviously, this time period is removed or interface transfer is removed. So, in this case, the total time will be taken by the system will be 40, that is memory fetch, plus 45, that is taken by the multiplier, and finally the adder operation, that is 15 nanoseconds. So, it comes as 100 nanoseconds. Now, in C part, calculate the speed up of the pipeline for 10 tasks and again for 100 tasks. It is very simple. You simply put the values of these values into this particular speed up factor formula, that is n Tn upon k plus n minus 1 times Tp. So, it comes as 1.67, because there are 3 stages. You can observe in this particular figure there are 3 stages, 3 stages are working in parallel. So, that is why k value here is used as 3. So, you may ask that how this k value comes as 3. So, this way we can understand, and for 100 tasks it comes as 1.96, and in D part what is the maximum speed up that can be achieved. So, like we have done in previous case, that S max equals to Tn upon Tp, that is 100 upon 50. So, it comes as 2. Now, next problem, it says various segments will take different times and interface register will take 5 nanosecond. So, we have to calculate total time to execute in case of pipeline system. So, here the tau max we have to calculate first, which is nothing but the slowest time period, that is 95 in this case, plus interface delay, that is 5. So, Tp or the clock period for this pipeline system will come as 100 nanosecond, and for 100 tasks you can simply calculate in this formula, that is k plus n minus 1 times Tp. So, it comes as 10.3 microsecond using the formula of k plus n minus 1 times Tp. Now, in second part it is asked how we can reduce this time period, which is equivalent to 1/2 of the previous case, or A part, what we have calculated in A part. So, how we can reduce this time period? So, here in this case we have to divide this segment number 3, which is the slowest one, into 2 parts if it is possible. So, we can divide this into 2 parts, either 45 and 50, or we can divide into 55 plus 40. So, this will be the feasible division of this slowest stage T3. So, if we have divided this particular third segment into 2 parts, that is segment number 4 and 5. So, here there will be 5 segment after this, after division of this. And what is the time period in this case? So, first we have to calculate the time period. So, if we have divided 45 and 50, so time period or clock period for this pipeline system will be for 50 plus 5, that is 55. And there will be extra, there will be one more stage which we have introduced. So, number of stages in this case will be 5. So, we can calculate easily the total time taken by this system for 100 tasks or n number of tasks. So, that will come as 5.72. Now, in next problem, consider a computer with 4 floating point pipeline processors, and suppose that each processor uses a cycle time 40 nanosecond. Each processor is taking 40 nanosecond. How long will it take to perform 400 floating point operations? So, it is very simple problem, since there are 400 number of tasks and it is a pipeline system and 4 processors are performing and each processor is taking 40 nanosecond. So, obviously, this will be 400 into 40 upon 4, that is 4000 nanosecond. It is very simple problem, and it is also asked, is there a difference if the same 400 operations are carried out using a single pipeline processor with a clock cycle of 10 nanosecond. So, very simple, there are 400 tasks and each processor is taking 10 nanoseconds. So, obviously, it will come as 4000 nanosecond, which is equivalent to the previous case. So, it is very simple problem. Next problem is, we have to draw a time space diagram for 6 segment pipeline showing the time it takes to process 8 tasks. So, 8 tasks we have to execute through this pipeline system having 6 stages. So, in left side you can see there are 6 segments or 6 stages, and we have to execute this. So, in first case, as we have already discussed, in first case this pipeline system will work as a non-pipeline system. So, you can see in first case it will take 6 clock cycles, and after that it will take 1 clock cycle to execute next instruction. So, in every case it will perform, or it will give the output of next instruction. So, you can see you can simply put the values of k, n and 1. So, there are 8 number of tasks and 6 segments, and TP is 1 suppose. So, it will come as 13 cycles. So, in 13 clock cycle it will complete, or it will produce the output. So, this way we have done all the problems related to this particular unit. Thank you.